A very good morning to all the participants and our distinguished speaker. I am Nilesh Marle, designated as Technical Superintendent, and on behalf of SAFE CRNTS IIT Bombay, take this opportunity to welcome you all for today's talk on TOF-SIMS Introductions and Material Applications, which will be presented soon by Dr. Andrew Jordan. Before we proceed, I would like to give brief overview of SAFE IIT Bombay. SAFE IIT Bombay was inaugurated by our late ex-Prime Minister Sri Morarji Desai in the year 1976. Department of Science and Technology DST has set up SAFE in various parts of the country with an objective of providing guidance for the data acquisition using sophisticated analytical instruments. This slide explains how SAFE and CRNTS were established over the year. Currently, Professor Anil Kotanthare is the head of the department. We have around 16 major equipments under SAFE and 5 major equipments under CRNTS. SAFE IIT Bombay provides measurement services to researchers from various academic institutes, national laboratories, and industries. The current slide shows the facilities at IIT Bombay which are funded by DST. We have upcoming dual beam focus electron and ion beam facility which is about to get installed. This slide shows the facilities at SAFE CRNTS which are funded by IIT Bombay. This slide shows the TOF-SIMS which is in-house at SAFE CRNTS. Workshops are held at SAFE for external and internal user. To get more detailed information about SAFE, you can visit us at safe.iitb.ac.in where information about all the instrument house at SAFE IIT Bombay is available. Also, you can get the procedure to avail these facilities. At SAFE, we receive sample from the state of all the India from our neighboring country Nepal also. We also encourage users from various academic institutes, national lab and industries to visit our facilities. You can also join us on our LinkedIn account to get latest update on instrument webinar or any upcoming event held at SAFE IIT Bombay. This is the brochure for the conducted webinar series. Information about this is listed on our LinkedIn page as well as on our SAFE website. All the instruments at SAFE IIT Bombay are operated and managed by dedicated staff. We would be very happy to welcome you all and help you with the analysis. Now, I would like to introduce our today's speaker, Dr. Andrew Jordan. Dr. Andrew Jordan is a staff scientist at Physical Electronics USA. He joined PHI in 2019 after 4 years at Samsung Astron Semiconductor. At PHI, Andrew provides TOF-SIMS instrument demonstration and contract services as well as develop TOF-SIMS material applications, software and hardware. Andrew received his doctorate in material science and engineering from Virginia Tech in 2016 with focus on SIMS technique development. So let's commence today's talk. Over to you, Dr. Andrew Jordan.
Thank you, Nilesh, for that introduction. I will begin to share my screen and present my talk.
An outline of the talk will go as follows. I'll say a few words about physical electronics and how the company is involved in materials characterization. We'll go into what is TOF-SIMS, the various components of the instrument, followed by why TOF-SIMS, so the advantages of TOF-SIMS and what it can offer to help solve your problem. And then we'll go into the analytical modes of TOF-SIMS. I'm going to tie it together with applications so you can see how the different modes and how they play together with the applications to really tie it together. Then we'll go into recent advancements in TOF-SIMS, followed by a summary. TOF-SIMS fit into the realm of chemical characterization. So this is a nice bubble chart by Evans Analytical Group. It really just is a really nice thing to show how all the techniques kind of work together and how they fit into this puzzle of materials characterization. So on the y-axis, we have the detection range or detection limits, and then analytical spot size on the y here. This talk is going to focus on TOF-SIMS, so you can get down to roughly 100 nanometer spot size with parts per billion detection, and you can also get chemical information, molecular and elemental information. Just showing how it fits together with OJ and XPS instruments and the information you can gain there. So what is time-of-flight secondary ion mass spectrometry? This animation will just show how the analysis or instrument works. Takes a pulse primary ion beam, it rasters the sample to generate secondary ions. They're extracted and then they travel through a mass spectrometer where they're separated out by their mass to charge. So lighter ions will hit the detector first, and then heavier ions will hit later here, as you can see in the mass spectrum. And so this talk's really just going to focus on several different aspects of TOF-SIMS. So we're going to focus on this solid ion interaction, different types of ion beams used to probe your sample or sputter your sample. We'll go into the different types of mass spectrometers. And so the goal of this talk is to show how TOF-SIMS works and the various components of it. So we'll get into the solid ion interaction. So this is a molecular dynamics simulation from Penn State, and it just shows the sputtering event of how the collision cascade and how secondary ions are generated. So at time 0, the primary ions coming closer to the sample, then at 20 femtoseconds, 75, and then all the way at 200 femtoseconds, you can see the sputtering event. And as this primary ion hits the surface or hits the sample, it generates this collisional cascade, and ions are produced, electrons are produced. The negative ions coming off the sample, as well as electrons, and molecular absorption will occur as well. One thing to note about the sputtering process is that vast majority of your sample of the ions generated are neutral. So you're only looking at a small percent of the material coming off of your sample. So some basic principles of the time of flight process. So it takes a pulse primary ion beam to bombard your sample. Secondary ions are generated. They're extracted at 3 kV, and the primary ion beam is pulsed around 5 to 25 kilohertz, generally around 10 kilohertz. And all the secondary ions are formed at the same time, essentially, time 0, less than 1 nanosecond, and they're extracted at 3 kV. So they're all traveling at the same, essentially at the same energy. The lighter ions will hit the sample first, or detector first, followed by the heavier ones. And the equation that relates to flight time is the kinetic energy equation, E equals 1/2 mv squared. And so solving for the time of flight, it's approximately the square root of the mass. And so after you have your mass spectrum of the analysis, you can easily calibrate the spectrum with at least 3 peaks. So calibration can be done very easily. One of the inherent issues with the time of flight or the sputtering process is that you, as a result of the sputtering process, you get an energy spread within a particular mass to charge of an ion. So you have an ion that's extracted from the sample, and as it comes off, you'll have it coming off with different energies, so different flight times. And so we need some way to refocus the kinetic energy of these ions so we can have better mass resolution. So this is just some work down here from Delcourt showing the spread, the energy spread of a particular mass to charge ratio ion. And so you can see the vast majority of the ions come off at one particular kinetic energy. And you can see this large tailing up to approximately 20 eV. And this tail here is what causes a loss in mass resolution or degraded. And so we need some type of instrumentation or some way to refocus this energy so that we can get higher mass resolution. Some other things that can cause a loss in mass resolution is topography. So you have the same ion coming off at different points in your sample, high and low, so it'll take different flight paths. And then also you can have charging, so different sample potentials will also degrade your mass resolution. So some of the ways that we can focus these ions to get better mass resolution is by using an energy compensating TOF analyzer. There are 2 main types of commercially available energy compensating analyzers. One type is a Reflectron, and so we have the same mass to charge ion coming off with different energies, and as it's being extracted, it comes in contact with this electric field with an ion mirror, and the high energy ion will take a deeper path into this ion mirror. The low energy will take a shorter path in it. And as it's being directed back towards the detector, they get refocused because of these different flight paths. Some things about the Reflectron: it's not intrinsically spatially focusing, so it acts more like an ion microprobe, not a microscope. The ion mirror is a low-pass energy filter, so you have increased spectral noise. The mass scale is linear over a small range, so if you're looking at a large mass range, you'll need known peaks throughout the mass spectrum to be able to calibrate it, and you have a limited solid angle of collection. Another type of energy compensating analyzer is a triple ion focusing time of flight mass analyzer, also known as the TRIFT, and this is what physical electronics sells. And so it works slightly different than the Reflectron is that instead of using a mirror, it uses 3 ESAs to refocus the kinetic energy of the ions here, and they work together to focus the energy. And so the ions take different paths through these ESAs to reach the detector. Some things about the TRIFT is that it was originally created as a stigmatic ion imaging. So you have spatially focusing. So early on it acted as an ion microscope. So your chemical information and position of the ions coming off of the sample were preserved through the ESA to the detector. And that was really important early on when stigmatic ion imaging had better resolution, the optics had better resolution than the spot size of the analysis beam. But that's not the case anymore, and so the TRIFT operates mostly in a ion microprobe because of the improvements in the ion beam. The TRIFT is a bandpass energy filter, so you have it eliminates post-source decay, so you get high signal to background. And the mass scale is linear over a large range, so you only need a few peaks to define a very large range of masses to calibrate. And you have a large solid angle of collection. So now that we've talked about how the ions are generated, how they're extracted, and the different types of mass analyzers, what kind of advantages can TOF-SIMS does TOF-SIMS have? What kind of information can you gain from it? And so advantages of TOF-SIMS is that you get detection of all elements and isotopes, hydrogen, helium, oxygen 16 and 18, etc. You can get molecular information, so organic and inorganic. You get parallel detection with time of flight mass spectrometer, so you get the full mass range. You're not just picking and choosing a few select species to look at. You get excellent surface sensitivity. The outer 1 to 3 atomic layers are 10 to 20 angstroms. You get very high chemical sensitivity down to the parts per billion range. The data acquisition is generally fast. It's in the minutes regime. And you can get, depending on the mode you operate in, you can get very high spatial resolution, so less than 70 nanometers in imaging mode with unit mass resolution, and 300 nanometers resolution with best mass resolution. And the real nice thing is that you can analyze all materials, conductors, semiconductors, and insulators, so you're not limited by the types of samples that you want to look at. How TOF-SIMS fits into the mass spectrometer regime is that it's an imaging mass spectrometer, and so that you get images as well as spectrum in for this technique. And how it works is that the primary ion beam rasters over top of the sample, and the computer, the electronics stores the position of the spectrum where it was generated as the beam rasters across the sample here. And so as it does this, it stores all this information, so you can generate a mass spectrum is generated at each pixel, and then you can it back to reform the ion image of the mass spectrum. And all this is saved, so it's really nice that you can do post-acquisition analysis of the data, and we call this retrospective analysis. So you don't need to know everything at once during the analysis. So you can collect your data not knowing anything, use it more as a survey technique, and then take the data offline and begin the process and break it down and try to understand your data better. And so there's 2 ways you can look at it and retrospectively is looking at the mass spectrum and generating images here. So from this red peak here, you can see the chemical information distribution from that peak, as well as the peak for just of this green one here, and see how these ions are distributed across your sample. Or you can work off of the total ion image and select regions of interest and look at spectra from there. So you can work both ways here to try to understand and interpret your data better. As well as TOF-SIMS has very flexible and adaptable sample mounting. So with the top mount holder, you can load all sorts of different kinds of samples here, just showing the wide variety, optical fibers, contaminated glass slides, contaminated polymers, bulk polymers, devices, paper, botanical sections, animal cross sections. And then there's a different type of holder, a back mount holder, and you can look at powders, intact geological samples, woven fibers. As well, there's a couple different sample mounting options instead of just loading your sample in there. So you can do a Zalar rotation, so rotating your sample, which can show some benefit for depth profiling to improve depth resolution. We have a temperature stage, so you can operate at cryogenic temperatures possibly for biological, analyzing biological samples, as well as going to high temperatures for diffusion studies possibly. And then we have a voltage/power cycling stage, so you can look at use this stage to do battery applications to look at failure of batteries. So all of this makes TOF-SIMS very flexible, so you can look at a wide variety of samples here, so you're not limited. The next part of the talk is going to focus on the TOF-SIMS analytical modes and applications. So it's going to be broken down into just looking at surface spectra, and then we're going to go into imaging mass spectrometry, and then we'll go into depth profiling and follow it up with FIB-TOF. And I'm going to really tie these together with applications so you can see the information you can gain from your sample in these different modes. So we'll go into analytical modes. Before we do that, we need to spend a little bit of time understanding the ion beam that's probing your sample to generate this mass spectrum. So there are three main types of analytical ion beams in TOF-SIMS. We have liquid metal ion guns, and it's essentially a field emission tip commonly used in FIBs. So it evolved from gallium, which is used in a FIB, and then it kind of evolved over the years to more of a cluster source to get different information to reduce fragmentation and preserve and to increase ion yields. So it went from gold to bismuth, and with bismuth you have high cluster selectivity, so you can operate from bismuth 1 all the way up to bismuth 7. So you get nice customizability of your cluster size. And then going into C60, which is a cluster source, you can get different information from there and really get higher ion yields and decrease fragmentation. And then going into kind of more of a newer ion beam is the large gas cluster. So you can get argon class gas clusters up to 4,000. So you can pick and choose what type of ion beam you want to use to generate your spectrum. But before you, after you choose your ion beam, there's one thing you need to know about TOF-SIMS is that you need to stay in the static limit. And what that means is you need to keep the primary ion dose low, and that ensures that a new area of the sample is hit. So you're getting chemical information from a new area of your sample, so it remains intact and pristine. So you're not getting your mass spectrum from damaged area or in that damaged area of the sample. And so what the static limit is it's defined as roughly a dose density of 10 to the 12 to 10 to the 13 primary dose of primary ions. And just for simple calculations, the atomic surface density is roughly on the order of 10 to 15 atoms per square centimeter. So less than 1% of your surface is bombarded with an ion. So all your information is coming from a pristine new area. If you go beyond the static limit, you begin to damage your sample, and you begin losing this molecular information that is preserved. The TOF-SIMS ion beams are optimized for this regime for operating at low doses, compared to the dynamic SIMS that are used mostly for depth profiling. So what does this static limit look like? So here is just some STM images of a silicon surface before and after sputtering. So this is a pristine surface here, so you can see very intact and no damage. After the surface is exposed to a dose of 3e to the 12 ions per square centimeter, you can see that you do have some damage from the analysis. As a whole, it remains intact and pristine. And so the static limit ensures the observed chemistry is undamaged and representative of the surface. But damage does occur from the sputtering process here, and I just really wanted to highlight the difference between using an atomic beam versus a cluster beam here. And so this is a molecular dynamic simulation showing the damage induced from a 15 kV gallium atomic source versus a 15 kV C60. And you can just see the amount of the depth of damage from an atomic at the same energy of a cluster source. Where with this cluster source, your energy per nucleon is roughly 250 eV, so it's much shallower and you can get much higher ion yields here using this a cluster source. And the residual damage from C60 is removed with the next sputter event, so you can actually get a clean surface that's undamaged by using a higher cluster source. So now finally getting into some mass spectrum here, and I just really wanted to highlight the detection limits of TOF-SIMS just by looking at a surface spectra. In this example here, we're looking at a mass spectrum from a NIST C1154 steel sample. You can just see as for this mass spectrum is from 0 to 100, and you can see all the different species present in the steel sample here. To highlight the sensitivity of TOF-SIMS, I just really want to point out that titanium is 0.004% atomic concentration in this sample here. And if you zoom into the titanium peak here, you can see that you get counts from it, and you can get excellent detection limits, so up to 40 pp parts per million with a detection limit of 50 ppb. So you can get excellent detection limits within a relatively short time here, 5 minutes. Another example is just looking at different polymers, so looking at the organic ion yields. So in these two examples here is just a mass spectrum of Teflon. It can be seen in any textbook from 0 to 150 here. This range, mass range, is generally referred to as the fingerprint region. So you can see all the different fragmentations from this polymer, as well as looking at an example of polypropylene, all the hydrocarbons. So now switching gears into imaging mass spectrometry, I'm going to show you some applications of it. There's kind of some neat ones. So this is how TOF-SIMS can be used in the pharmaceutical industry, and so it can be used to look at the drug distribution in animal or in delivery in body parts, particularly the liver. And so this is a drug distribution of a rat liver cross section, and it's collected with the C60 ion beam here. And so just looking at the secondary ion image here, this is the pharmaceutical molecular ion. So you can see how it's distributed in the rat liver, as well as this phospholipid here, just showing just the matrix of the material, so you can get an idea of how the size of the rat liver and the area of it. One thing to note here is this is a rather large image, so 19 millimeter, which is rather large compared to most of the images are acquired with hundreds of microns. And how that's accomplished here with TOF-SIMS is it's done with the Mosaic mapping. So the sample collects a field of view roughly anywhere from a couple hundred microns to 600 microns, and then the sample moves underneath the ion beam to a new area and performs an analysis. And it just repeats this until it completes analysis of the defined area, and it stitches it all back together post-processing. So as well as doing very small micron area sizes, you can do up to millimeter areas to really map out your sample and gain more information more on a macro scale. And we kind of touched on the different ion beam sources and how they can generate different information here. And I just really wanted to highlight the use of C60 here for this particular analysis, that you get the ion peak here that's representative of the drug molecular ion here. And then we're looking at it with a 30 kV gold 3 here. You can see it's barely here present due to the fragmentation, not much difference from the background. But then if you look at it with an atomic gold, you can see that it's completely fragmented and disappears. So depending on what you're trying to look at, you need to pick your analysis beam correctly. And I just really wanted to highlight that. Another example of how TOF-SIMS can be used is imaging looking at different chemicals present on hair for the shampoo and condition treatments. And so looking at positive ions here of the hair, it's roughly about 125 microns in diameter here. And we can see from the positive SIMS here, looking at calcium, how it's present on the surface, as well as this hydroxyl group here, just its presence. And then some ions come off better as negative versus positive, so you can look at different polarities to gain different information about your sample. So in negative mode, you can see the CNO here, and then sodium lauryl sulfate, a common chemical used in shampoo and conditioner, and how it's distributed over the hair, as well as this fatty acid. And I really want to take note here that these aren't flat, perfect samples. They have topography, they're rough, they have different depths, that you can still gain good information from these samples. Now moving on to how TOF-SIMS can be used in a completely different industry, such as the ore mining process. So this example we're going to look at is the chemical residue left on the ore mining particles, and it's used in froth flotation. And so just a real quick about froth flotation. It's a refining process that utilizes the hydrophobic properties of material for separation. The hydrophobicity can be increased by treating the material with different reagents to separate different materials out, such as iron or copper. It's widely used in wastewater treatment plants, oil refineries, and ore mining, as we're showing here. So you feed the material into, looking at this cartoon, you feed the minerals into this bath. It's agitated and with air, and it spins around and generates these bubbles, and your hydrophobic material attached to these bubbles rise to the top and then are separated out, and the hydrophilic material separates to the bottom. So you can separate out your different particles just based on the hydrophobicity of the material. So looking at some of these minerals that were treated with different chemical reagents and separated out from the ore mining process here. So this is a chemical secondary ion image of minerals of iron, copper. So you can see their distribution. And these aren't flat samples. This is a scale bar is roughly 100 microns here. So you can see the distribution of iron and copper particles, and this blue background here is just the sample amount of indium. So these particles are pressed into an indium amount, and that's in positive mode. And then looking at negative, you can see the distribution of oxygen on these particles as well as sulfur. And since we talked about retrospective analysis, so not knowing anything about your sample going into it, so you can look at these chemical images just to see which particles are copper or iron, and then we can look at the images and then go to the mass spectrum and see if we can see any different peaks that correspond to the different complex reagents that were used to separate it. And so highlighting in green here the copper regions, so you can see the mass spectrum generated from these areas and the peaks associated with it, as well as looking at the iron particles here and looking at the spectra from that. So you can go from the images and work and generate mass spectrum to see which phases, which peaks are associated with the different particles. So it's a very nice way to look at use TOF-SIMS to analyze flotation agents. So moving on to depth profiling, another area of TOF-SIMS where we can gain information as a function of depth. In TOF-SIMS, you can have a large variety of sputter ion beams here. So generally, a TOF-SIMS is equipped with at least 4 to 5 different ion beams. Oxygen used to sputter will enhance electropositive species, such as your metals. Cesium can be used to enhance electronegative species, such as oxygen and fluorine, as well as argon, just as a physical sputtering. And then C60, commonly used for mixed materials. It shows less preferential sputtering between inorganic and organic, so depending on your material. And then gas cluster ion beams to sputter work really well and have high sputter rates for organic materials and are less effective at sputtering inorganic. So if you have a mixed material, you probably don't want to use argon gas clusters. So we'll go into showing how this how TOF-SIMS does depth profiling. And since it has multiple ion beams, you can use your LMIG or your primary ion beam to generate the spectrum, and then you can switch to a different ion beam to sputter to either enhance or remove the material at a faster rate. And so with TOF-SIMS, you get the benefit of having a separate analysis and sputter beam. And this is in contrast to dynamic SIMS, where your sputter beam is your analysis beam. So you don't have this choice of picking and choosing. And so as a result of this, you get a low impact sputtering event with high mass resolution, and you can have a low impact sputtering event with high mass resolution. In the sputtering beams, as you go down in energy, you get it's harder and harder to focus due to the space charge effect. And so having high spatial resolution with low energy, it can be rather challenging. But we can overcome that by using a pulse analysis beam to a high energy analysis beam to image with good spatial resolution. And so how this is accomplished is that analysis beam hits the sample, turns off, and then a DC beam of low energy, high dose removes material, and that material is thrown away and then turned off, and then the pulse analysis beam comes back on. This is repeated until you go through your desired depth of interest. Some of the applications with dual beam depth profiling is interface analysis. So it looks like a simple depth profile, just 120 nanometers of molysilicide on silicon. And how this is accomplished, this depth profile is generally accomplished with dynamic SIMS, is that you just pick your couple species of interest. If you were looking for something that you didn't know was there, it would be very hard to find retrospectively. But with TOF-SIMS, you can do this a little bit differently and approach it as a survey. So just looking at the depth profile generated here, we have silicon-30 as our matrix material for the substrate, and we have molysilicide as the layer marker for the molysilicide layer. And so one of the nice things with TOF-SIMS, since you can do everything retrospectively, you can look at different the spectrum that are generated at different points in the depth profile. So looking at in the molysilicide film, you can look at this mass spectra generated from it, oxygen, silicon, silicon nitride, and molysilicide here. 28 silicon and 29 aren't present, and dimers blank just to protect the detector while they're not present in the spectrum. Now looking at the mass spectrum generated at the interface, you can see carbon's present, fluorine, silicon carbide, SiO2, as well as the molysilicide. So now you can select these peaks that are present and replay a depth profile and see how these species are distributed in your sample, not knowing what might be present there at all. And so now you can see how carbon, you see elevated carbon, oxygen, and fluorine are at the surface. And this would be more difficult doing it using a traditional dynamic SIMS because you have to select your peaks going into the profile beforehand, compared to TOF-SIMS where you can look at everything on the back end. So it's very nice for using it as a survey depth profile technique. So another application of depth profiling with TOF-SIMS is looking at the composition of aerogels. So a mixed polymer with organic and inorganic components. And so what an aerogel is, it's a porous, ultra lightweight, low density material with extremely low thermal conductivity. It's created by combining a polymer with a solvent to form a gel, then removing the liquid from the gel and replacing it with air. So it's a very lightweight material. And one of the interesting things about aerogels is they're used by NASA to insulate the Mars installation on the Mars rover. And this image over here on the right is just showing the extreme thermal or low thermal conductivity of the aerogel. So you have a Bunsen burner or a torch underneath an aerogel with crayons on top of it, and you can see that they're not melting. So just highlighting the extremely low thermal conductivity. So in this example, we're going to be looking at profiling an aerogel with two different types of ion guns, a C60 and an argon. And this is an aluminosilicate aerogel, so it should have a uniform stoichiometry between aluminum and silicon throughout this material. And as we go through the 6 microns of the aerogel with argon here, you can see that the aluminum signal remains essentially flat, but silicon starts out high and then begins to degrade as you go to the interface, as well as carbon, and they should be uniform. And you see copper contaminated at the surface, and then it starts to begin here. And so it's kind of misleading and leaves you to not know if this is the true composition of your sample. As well as you can look at the optical image of the crater here, and you can see that the sample is not transparent as it once was, that you get all this sputter-induced roughening and it distorts the optical image here. So you can see that roughening is occurring from the sputtering. And this is with 5 kV argon. So if we looked at it with C60, which has been shown to be very well at sputtering inorganic and organic materials very well. And so now looking at it with C60, you can see you get a nice uniform flat signals of aluminum, silicon, and carbon. And you can see that copper is present at the surface, but then it creeps up towards the interface here. So you get a more uniform depth profile using C60 compared to argon. And looking at the optical image, you can see that the crater is not black, so it's a good sign that there's not any sputter-induced topography. So this looks like it's more representative of the actual sample. So then putting it together just to showcase the difference in the signals here between argon depth profile and C60, you can see the argon profile here, this aluminum silicon ratio as it degrades as you sputter, compared to the C60 where you get uniform flat traces. So you kind of need to know a little bit about your sample and what guns you're going to use to sputter it. Another example here is learning from nature, so then analyzing a damselfly wing with TOF-SIMS. So the damselfly is native of the Brazilian rainforest here. And looking at the wing, you can see the different color regions on it. The real big question is trying to understand what's causing these colors. Is it a layer thickness? Is it different chemistries? And so TOF-SIMS was used to analyze a damselfly wing to learn about it. And so looking at these different regions here, the backside of the wing is a red color. The different regions here have different layer thicknesses, so roughly 180 nanometers for this yellow-green area, 195 for the red area, and 145 for the blue area. And the backside of the wing is red, and you can see that it has the same layer thickness. And so the big question is, what is the chemistry of these layers? And so gas cluster argon was used to depth profile these materials because it's organic, and try to see if we can identify what the chemistry is in these layers as we go through the wing. And so the depth profile was accomplished or taken in a positive profile mode, and another profile was generated in a negative profile mode. So looking at the positive one here, you can see that this is just a summation peak in green here of the amines, just to highlight the different layers of the film of the sample here, as well as sodium and potassium are used. So you can see the different periodicity in these wings here as you go through it. And just comparing this to the actual SEM image here, you can see that they're in good agreement that you see the different layers and the different species associated with it. And then looking at it in negative, you can get different ions will come off with better you can use different ions to generate different information from your sample here. So looking at CN and CNO for these different layers indicators. But as we discussed earlier, that you can always look at things retrospectively, and so you can break down and look at different aspects of this depth profile and look at the mass spectrum generated with. So we're going to look at spectrum A here, and the hypothesis was that there was different levels of melanin in this wing that causes the different colors in it, and so it was compared, the layer A was compared to a melanin reference, and you can see just how good agreement they are here, looking at the melanin reference mass spectrum, CN, CNO, C3N, as well as the various different CN fragments here. And then looking at layer A here, you can see CN, CNO, and look, the peaks line up and match very well. So you got a good agreement between the reference and layer A, showing that melanin is present in here. And what's not shown is the different layers here, and they have various levels of melanin compared to layer A and the reference sample here. That was just a depth profile looking at it that way, and then looking at the mass spectra. But then also you can reconstruct this, because at every depth an image is generated, since we have a mass spectrum at every pixel, then you can reconstruct it and look at it in 3Ds and generate 3D information images and show how the information is distributed in depth with an image. And so looking at the positive spectrum here, you see the surface of the wing here. And as well, we're comparing this with the TEM micrograph here. So these scale bars, 500 microns here, and you can just see how well this 3D image matches with the TEM image. And so you have the wax on the surface here, followed by the various amines summed in this layer and the sodium, and see this alternating structure, as well as looking at reconstructing the profile in negative mode, looking at the wax on the surface, CNO and CN, and just seeing how this is distributed in depth here. So it's very nice that you can look at individual images, as well reconstruct depth profiles, and look at mass spectrum and see how they can correlate with TEM. So TOF-SIMS offers a very powerful tool to analyze your sample, even in the biological or organic world. So we've kind of highlighted the different sputter gun options, so what you can use to sputter your sample or to analyze your sample. And so there's some kind of material dependence on the type of ion beam you want to use, so what kind of information you want to gain. So with oxygen, is primarily used for positive SIMS, so enhancing electropositive species. Cesium can be used for enhancing negative species by orders of magnitude, as well as C60 can be used, as we've shown here, with excellent sputter rates for organic and inorganic, so mixed materials. And then shown with the Damselfly example that you can use gas clusters here to sputter through organic material very well. So you really want to know what kind of samples you have and what type of analysis beam or sputter or analysis beam you want to use to generate your information. So going into the last bit of analytical mode of TOF-SIMS is FIB-TOF. And so you might be asking, well, I can just do a traditional depth profile going from the top down, but there's some issues associated with doing a top-down depth profile, several artifacts that can be caused just by doing a depth profile. And so another ion beam choice you can have to your selection is a focused ion beam used for milling. And that's just what's very similar to what's used in a FIB, gallium liquid metal ion source here. And so why 3D FIB-TOF imaging? Because traditional depth profiles have differential sputtering, you can accumulate beam damage, as we saw with aerogel, and you can have slow sputter rates and long acquisition time. So these can all be mitigated by using a FIB-TOF analysis. So how that's actually accomplished in TOF-SIMS is that the FIB gun is orthogonal to the LMIG here, and so you find the area of interest that you want to look at, and then you begin milling it out, and then finding your particular area, and then imaging it, milling it, imaging, milling it, and just repeating this until you go through the your desired thickness. And so what's really nice about TOF-FIB is that you're not moving the sample between removing material and imaging it, so you don't need a lot of fiducial markers or any really to reconstruct the data, so it's very easy to look at. So in this example, I'm going to show is a FIB trench, is a copper tungsten alloy, and so just looking at the cross section of this FIB trench here, this is a 60 by 120 micron FIB trench here, and this is a secondary electron image from the ion beam here, and so we want to find the area of interest here, and so we're going to look at this cross section here. And so that was before, and this is after. So the amount of material that's been removed is about 10 microns in depth. And so we chose a 20 micron by 20 micron field of view. So our field of view would be 20 by 20 by 10 microns. So this is a relatively deep depth profile that we're looking at here with this FIB TOF image. And so now reconstructing this, this is the Z direction here going down and into the sample here. And you can see the reconstructed 3D image depth profile of the distribution of copper in the sample here, and just see how the various grain orientations of it and the non-uniformity of it and how it's preserved. And just looking at a different top-down version of it, so you can see how the grains are in this alloy, as well as looking at all the different other materials. So this was a copper tungsten one, so looking at the copper tungsten distribution, so you can just really see how they're mixed here. And this information might have been lost doing a traditional depth profile, because you can have a preferential sputtering between copper and tungsten, or you can get roughening that would disturb the chemical information and how it's distributed in depth. So this FIB TOF method is a nice way to look at, to preserve the information by milling it out and imaging it and then reconstructing the profile. Some recent advancements in TOF-SIMS started in 2016 with adding MS-MS option to that. And so what that is instead of doing your traditional MS1 spectrum, what we've been looking at here is that there's a separate mass spectrometer attached to the TRIFT, and it selects, as the mass species are traveling through, you can select a particular mass to charge ratio ion and then send it through a collision-induced cell, a dissociation cell, and then further fragment. And so you can look at the composition of particular high mass peaks here. And so this allows for unambiguous identification of peaks, which is really nice, because without this, you're kind of using best guesses and trying to look at different other fragment patterns to identify this. But this MS-MS option allows you to really identify with high confidence of what this peak is. And so the need for MS-MS is, as you go to higher mass to charge ratio ions here, it becomes more and more difficult to correctly identify them. And so that's why we need this MS-MS, and why it's a nice option for identifying high mass peaks. So just one example of how MS-MS can be used to identify unknown contaminants in a sample here. This is a mass spectrum, or an image, secondary ion image of a common lubricant used in industry. And this is the mass spectrum of it in the image. And so it looks like a simple one single component species or sample here. Get the high mass peak at 284, and this 256 peak looks to be an alkene loss peak. So everything looks normal, looks to be simple, but however, trying to identify this 284 peak here can be rather difficult. So this is just within the software, you can generate a list of combinations of what this peak might possibly be, and see the deviation and the error in ppm, and see how accurate this actually is. So going through this, you would probably select the lowest error, so with 13 here. However, knowing the answer retrospectively, it's this mass actually is the correct choice here, this octadeca animate, but it has the highest error here, so you generally wouldn't pick this just off looking at a mass spectrum alone. And so what we can do is send this 284 peak through the MS2 detector and collect the fragmentation pattern of this 284 peak to see what the 284 is composed of. But in addition to generating the MS2, you get to collect the MS1 data in parallel. So you get two sets of mass spectrums here. The MS1 set here, which we just saw on the previous slide, as well as the MS2 of the fragment pattern of this 284, and look at all these images generated from them as well. And so just looking at the main two peaks in this MS2 one, we can look at the generate an image from this spectrum here and look at the distribution of mass to charge 88 and see how it's distributed. You can see that there's some gaps here missing it, so science suggesting that there might be a two-component piece to it, as well as looking at this charge 60, and it seems to be the other component of this sample here. So we've identified two components with this MS2 spectrum here. And now with the MS2, you can look at the spectrum generated from each region from the image here. So the red spectrum correlates to the red areas in this image, and the green, which appears to be the substrate of the true material here. And you can see that these two spectrums are drastically different. And the nice thing with MS2 is that you can use it to compare with other MS libraries, and they match very well. And so comparing the red area mass spectrum with the NIST database here, we've confidently ID'd it as hexadexyl trimethylammonium, and the green area as dodecaanimid. And so now we went from one mass spectrum generating 2 with the MS2 to confidently identifying these 2 components in this unknown sample here. And so it's a very nice way to confidently ID some unknown materials in your samples that will otherwise be very difficult and could take a long time. So just some of the strengths of TOF-SIMS, you get detection of all isotopes and elements. You get parallel detection, so full mass spectrum. You get you get very shallow you get high surface sensitivity, so just the top to the surface, 10 to 20 angstroms. You get high chemical sensitivity down to ppb range, high spatial resolution, and high mass resolution, depending on the mode. And you can analyze all materials, conductor, semiconductor, and insulator. Some of the limitations of this technique, it's not perfect. Quantification is problematic. A lot of the examples I've shown were organic, so it's kind of hard to generate known standards of organic materials. Part of the sputtering process is that the ion beam limits the detection of high mass peaks because of fragmentation. So getting up into the thousands of AMU becomes rather difficult because of this fragmentation just of the sputtering process. And I don't know if I mentioned it, but all of this occurred in ultra high vacuum. So if your sample is not ultra high vacuum compatible, it can be an issue. But there's some ways to kind of go around that and mitigate it, is operating at cryogenic temperatures with the different stages. And just comparing TOF-SIMS to dynamic SIMS, you have reduced sensitivity, just looking back at the bubble chart, and your analysis time is increased compared to dynamic SIMS. So there are some drawbacks to this technique compared to the others. Since this was a one-on-one talk, I just wanted to just show some of the reference materials out there if you wanted to further learn about TOF-SIMS, so you can refer to these as well. And so I'd like to conclude and just say thank you all for listening in and tuning in to this webinar on TOF-SIMS.
Thank you, Dr. Andrew. That was an informative talk. We have certain questions lined up for you. The first question is by Shivani Parekh. She wants to know about separation and identification of each component in an organic mix.
Say it one more time, please. I don't know if I caught it all.
Separation and identification of each component in an organic mix.
Okay, so just by doing the TOF-SIMS analysis, since it rasters over the sample, you can do localized, look at particular organic peaks, and then look at their spatial orientation in their image, and go about it that way. Kind of how I showed in. Let me share my screen here. Right here. So you can kind of work your way backwards by looking at particular peaks that are known to the organic sample, and then look where they're spatially located in your sample, and go back and forth to understand more about your sample and those location of organic peaks.
All right. Another question is by Dr. Vijay Karki. He would like to know about the molecular second ions are coming from the sample surface present in the sample or formed during the sputtering process. How can we say about that?
So this is maybe a more highly debated SIMS area, but there are two main areas or theories. One is that it's generated, this molecular MCS plus is the main mode, is that it comes from above the sample surface, I believe 5 angstroms if I call the papers correctly. And so it decouples the sputtering process from the emission process. So that's one theory. And the other theory is that it's a 2-sputter event, so that as you bombard your sample, the primary ions become implanted in your sample, and then the next sputtering event, they become ejected. So it decouples it from the initial sputtering process. So those are the two main theories on this molecular ion yield for MCS plus.
All right. Another question is by Professor Brij Mohan, who would like to know what are the precautions or errors in the depth analysis of impurities like boron, phosphorus diffused in textured substrate used for silicon solar cell silicon?
Okay, I think there's a couple questions there. Some of the issues, I guess, is using that sample is textured. So I'm assuming it has topography to it, and so you'll have your analysis beam or sample signal will be coming from different depths in your sample, so that will degrade your mass resolution. So that can really alter your implant or trying to understand where the boron is coming from in that exact sample. So ideally, you would love like a smooth sample, some way to eliminate some of this topography from this.
Yeah. Thank you, Dr. Andrew, for answering the questions. A special thanks to our head, Professor Anil Kutantaral, for initiating a webinar series of instruments housed in CRNTS IIT Bombay. We would like to thank the webinar and IT team for their valued support. A feedback form has been shared in the post. Kindly fill it. Thank you to all the participants for making this event successful. Stay healthy, stay safe. Have a nice day. Thank you.